pointer. Okay, let's start again. So we'll be quite fast. So we just explain what we are doing now in Trieste in the context of the GW method for the simulation of photoemission spectra. Just a brief description of what we are doing. So first of all, just wanted to introduce what photoemission experiments are and how they can be simulated by first principles. So, in photoemission experiments, essentially in direct photoemission experiments, your sample is having a process in which incoming light, in most of the cases synchrotron light, is impacting the sample and n photon is emitted. Then the momentum and energy of that photon are measured, and so it's possible to get insight in this process. In particular, what we are measuring are quasi-particle energies. Quasi-particle energies correspond to difference in the energy of a system where an electron is being added or removed. No? So, because indeed the incident light is emitting an electron, and so we are considering difference in energy of in a system which can be excited where an electron is being added or removed with respect to the energy of the system with a neutral number of atoms. So, if you want, if you'd like to calculate something like this, we should be able to calculate the energy of an excited system where an electron has been added or removed with enough accuracy. And then we will see. So we see that here also because. So starting from the talk we had before, to calculate excited energy of a system is quite difficult. So we will see how it's possible to calculate these quantities through another framework, which is called many-body perturbation theory. And then we will see how many-body perturbation theory has to do with the difference in energy of a system, or excited system with a number of particles n plus minus 1 with respect to the ground state energy of the system with a neutral number of particles n. Okay. Just to show that. So, photoemission experiments are measured has been a lot of improvement due to the introduction of synchrotron. This is the synchrotron electron in Trieste where I'm working. Trieste is just under this hill, and this is here, that is the Slovenia coast. So, in particular, I will show just in the next slides some spectra. They are being calculated in the gas phase beamline, which is this one. And in this way, we can access to essentially to the valence density of state using synchrotron ultraviolet light. So now, we have done this experiment on an organic molecule just containing essentially S and P electrons. So we don't have the transition atoms inside, transition metal inside. And what we are assessing is the valence density of state. So now, one could ask if you want to compare the valence density of state measured through synchrotron light and the result from valence density of state of a simple molecule calculated through density differential theory, let's say in the LDA or GG approximation. How do they compare? So, do you expect that you get good result with just with the LDA? This is just for the valence density of state. No, you don't have to assess excited state through LDA. Just we want to assess the valence density of state. So, the result indeed is this one. this is the molecule we are referring. This is called tetraphenyl porphyrin, just a simple porphyrin. This is porphyrin ring with no metal inside, so the simple stage. We just have 4 benzene groups which are attached at the angle that here you can see is 90 degrees. And here, so this green spectrum here is the measured valence density state. This measured photoemission experiment, the ultraviolet. This red line is nothing else than the LDA, the LDA valence density of states, and they've been, to better agreement, let's say, they've been just arbitrarily aligned at this feature here of the spectrum. So you see that the result, just for LDA, is quite poor. This is very simple. Just we want to set the valence density of state, and you see that also in a simple molecule, non-metallic atom present, so just the SMP electrons, the result for LDA is quite poor. And this is quite a trouble if you want them to help experimentalists in analyzing such spectra.
What is the denaturation energy for such molecules?
So?
Denaturation energy.
Ionization energy. Yes, very good. As you know, the first peak in the photoemission experiment, this one, the experimental one, correspond to ionization potential. Now, in this experiment which is done, the absolute scale of the spectrum correspond to the Fermi energy of the analyzer, and in particular they have not the data that they have given to us were just on this arbitrary scale of the energy, Fermi energy of the analyzer. There are others, so it can be aligned in a lot of ways, and the absolute what you get is that also, of course, the ionization potential calculated directly, taking the HOMO value of the LDAs, is also of some EV. Okay. The ionization potential here, I think the experimental value is around, there will be in the following lines, I think around 6.5 EV. So we have to use ultraviolet light.
These molecules are having by nature in the metallic side or in the semiconducting or in the insulating?
It is. No, this is an insulating material. I mean, you have the potential around 6 EV, and I don't know if I don't know the value for electron. I think if it is positive, it will be around a few tens of EV, so at least less than 1 EV. Okay. So we've seen that LDA is not enough to do what we want to do. So one possibility is that to use many Bradley functions. And now we have to see why many Bradley functions are related to quasi-particle spectra. So this is just for getting an idea. So the one particle Green's function can be written like this. So this is the mini-body ground state of the neutral system with n number of electrons. 0 means that is the ground state. And we have to take the station value of this operator, where T is just an ordinary operator, in the sense that if time T1 is larger than T2, we can write this operator just psi R1, and then here we have psi dagger. Otherwise, if the time is inverted, if T2 is larger than T1, we have to invert the 2, and also a sign, a minus sign here, so we have a plus I here, okay. And then there are operators, and then they obey anti-commutation relations. So this is the relation for the constructor of a particle at R2 position times T2, and this is for the annihilation of the particle of an electron at position R1 at time T1. So, and then we remember that we have this time evolution for the operators. We just, I think that we have done this before. The simple idea is that you can just replace the time evolution of the operator in the many-body green function, as we have done here. And here, now, we can do two things. The first thing that, so we've just chosen here for simplicity the case in which T1 is larger than T2. And you see here, we add an electron, no, at time t equal to 2, so that at this position here in this formula, we can just, no, we can just add, multiply for the identity operator. We can write in this case as a sum over all the states, no, the ground state, all the excited state of the system where an electron has been added. Which is interesting because doing this term, we can act, no, on over the. It's not working much. Okay. Someone another point. It's done, but slow. So okay, then we can act directly with this term here on the many body states, and then we get here this term, the term that we want, so that the energy of the system, static system at the state I, we have here a sum over all the states, the system where an electron is being added. And this is essentially what we want to calculate. Okay. This is just some operator algebra, so you don't know how to calculate it. What is happening that then, if we calculate on the formula that we have written before, the Fourier transform on the frequencies, like here, we will see that we can write the green function, on particle green function, many body one, on in this way here, with this AI, are the so-called quasi-particle amplitudes, which are defined like this, and this function as posed at the differences in energy of the system, certain system where an electron being added or removed with respect to the ground state of the energy of the system where with the neutral number of electrons. So essentially, the poles of this function correspond to the quantity measured in a photoemission experiment. Okay, but now we don't know how to calculate this function. Indeed, so up to now it was just many body, let's say many body field in this term, and now we have a way to access to this property is the way of perturbation theory. The idea is that, let's suppose we start with a system of non-interacting electrons. No. System of non-interacting electrons, the green function, it can be written simply like in this way. So simple, these are the state, non-particle state of the system non-interacting electron, and these are the corresponding eigenenergy. This is, for example, concerning Newtonian. Will be the starting point, we will see. And a system like this, no, we can think that we introduce a perturbation, and this perturbation will be the turning off of the electron-electron interaction. So if you want, we can think of starting from a constant, no, Hamiltonian, we switch off the exchange correlation potential, and we switch on the electron-electron interaction. Now we treat this interaction with perturbation theory, so this data in many-body perturbation. In particular, the green function, this is the many-body one, the one that we would like to access, can be written in terms of a Dyson equation, in which appears the green function of the non-interactive system. No? In our case, it will be the function one. And then also another term, which is called the self-energy. Now, the self-energy, indeed, indeed now the the difficulty of our problem is just embedding in calculating the self-energy. So for the moment we have done nothing, but we just reformulated the problem in finding approximation for the self-energy. So we just see that this equation corresponds to this other equation, just to read, which is the equation of the motion of the green function. And now we can introduce the so-called Chidao approximation, that will be a simple approximation which permits to assess the pose of the green function.
Is this self-energy is like Hartley energy, or what is this?
No, the Hartley term will be calculated in the LPA approximation. Just
what is the origin of this self-energy?
the self-energy.
Can we see?
Yeah, the origin of self-energy will be the sum of all the diagrams that you cannot be just cut one single one single green function line. This is the origin of the self-energy. This is the okay. So and this is how it works. So in this double approximation, we have this equation for the quasi-particle amplitude, and so this is psi n here at would be an approximation to the quasi-particle amplitude we have seen before. This is nothing else that the Hamiltonian of the starting non-interacting system, and then we act in two ways. In one way, we use the non-interacting system for calculating for providing a first estimation on the quasi-particle amplitude, which would be nothing else than constant state, and also the ingredients, so let's say the energies, which would be the constant energy, in order to calculate an approximation of the self-energy, which will be written in terms of two terms. One is a green function, will be the green function of the non-interactive system, and then a screened interaction, which will be calculated through the RPI approximation. And here, more precisely, this is just the steps, the final step that we have to code. We have to code in the computer code. So this is the simplest of the simplest approximation, introduced in this paper of Albert and Louis more than 20 years ago. It's very powerful. It's a very good result in obtaining this simple theorem. First of all the quasi-particle energies, En, are obtained by solving this simple self-consistent one variable equation, in which En here is the energy of the constant state. Here we have to take the expectation value with respect to the constant state n of the self-energy, calculated with the GW approximation. And then you see here, this depends self-consistently on the final quasi-particle energy. And then we have to subtract the expectation value of the exchange and correlation potential. And we see, as you see here, what we are doing, what we are assuming here is that the Constant eigenstate are good approximation for the quasi-particle amplitude, and this is a good approximation for the valence state. This is quite good approximation for the valence state. Then here you see the self-energy is appearing, and this can be written as a product of two terms, convolution to term in energy. So of the green function, the non-interactive one we have seen, and of the screened Coulomb potential. The screened Coulomb potential can be written in terms of the bare Coulomb potential and of the screened susceptibility, or the screen polarizability. The screen polarizability can be, as you have seen in the lecture before, can be found by solving a Dyson equation, which is very similar to see before, and the bare polarizability of the irreducible polarizability by 0 here is written as a convolution of two green functions. This is the RPA, random phase approximation, and the green functions are the same of the green function we have seen before. Just here for the rest I'm using psi to indicate in constant state. Okay, this is the scheme, no? This is just, you can implement it in any code you want, but there are two limitations. So, first of the limitation I have to say that this is working quite well. You can simulate for the emission spectra with this simple scheme quite reasonable way. But we have two limitations. So it's very computational demanding, because there are a lot of matrix operations, so it costs a lot. And then, as you see here, starting from this point here, you see here we have to sum over all the constant states, so meaning on the valence, also over all the conduction states. And this conversion with respect to these sums over conduction state can be quite cumbersome. Essentially, it's the same problem we had before for time-dependent DFT.
What are these quasi-excitations physically could be? Like there are various excitations in.
No, we just consider electronic excitation.
Only.
Yeah, just for the just electronic excitation.
But still, you are telling that this is quasi because it originates not from the reality, from the density fluctuation. Why you are associating with quasi?
But this is the terminology essentially, because indeed just when other electron is moving the material, it will feel the presence of the other electrons. So, and this is the okay. Just to focus a moment on this problem of the sums of the conduction states, it's also because most of GW coding usually use sums of the conduction state. Here we consider a simple system, just a benzene molecule, you put it in a cubic cell, and you want to assess the ionization potential. So we will not describe the technicalities of the code, but this is just to understand how this problem of the sum of the conduction state important is. So on this, here we report the ionization potential. So first, maybe I forgot that the ionization potential corresponds to the HOMO level calculated to the GW approximation to the mini-particle operation speed physics. So this is very important because we can test with respect to experimental results. In this case, benzene, we calculate ionization potential, so position of the HOMO level with the GW approximation, for a set of calculation considering an increasing number of conduction states. This is in electron volt, the cutoff, which is telling how many conduction states can be used in the calculation. So these triangles correspond to a calculation of 1,000, 2,000, and 3,000 conduction states. So the black line is the experimental value. The blue line, no wait, and this red line is a PBE result, just taking into consideration the HOMO value for the PBE. So what we want to focus here is that you see the convergence is, first we are very far from convergence, and then it also is very slow. No? At the point, the only thing was possible to do was just to fit with a formula like here, just considering the the lowest order term in the denominator. So that's very clear. And if you would like to be in this order of convergence, the extrapolated line is this blue continuous line. If we want to have accuracy like here, which is accuracy around maybe 0.1 eV, we should use a cutoff corresponding of 300 electron volt, which corresponds to a number of conversion states around 10,000. It's quite undoable. So this is a big problem, and then we would like to solve. So here I just maybe 15 minutes to finish.
Why are we interested so much in the benzene molecule to know its iron?
No, it's just an example. An example of the easiest system where essentially everything is supposed to work well.
Otherwise, does it have any practical implication in terms of fuel or something? Because benzene is also used in fuel.
No.
Can you infer anything from this study?
I don't know. It's just wanted to consider, to check the method and if the system was interesting. I think was by a choice determined, randomly determined. But okay, there's a lot of literature. Maybe this as benzene as some technology important, there are a lot of data on benzene, so it's worthwhile to have to consider a system where there is a lot of data available. There is no other motivation. So, and now I just explain how our method has been constructed. First of all, this method is split in two parts. One is the calculation of an optimal representation for the polarizability operator, for the basis for the polarizability operator. And this is important because of this. So let's suppose we want to calculate polarizability, this is irreducible polarizability. As you can see here, depends on two indices. And this means that to represent a matrix like this, we need a lot of terms. But if you just an object like this can be represented with enough accuracy, just with a limited set of this basis function phi alpha, and then a huge speed up can be achieved. Indeed, by definition, the same basis can be used for representing also the reducible polarizability, and also the basis multiplied with the Bayer-Conley operator can be used to represent the screen interaction. So everything then can be recast in a problem of matrix operation, where the dimension of this matrix can be strongly reduced.
What is the basis here?
The basis function is a phi alpha that we want to find. Phi, yeah. So you see, this phi alpha, if you have a limited number of them, you can just represent this operator with enough accuracy. This is a supposition we do. But if we can do this, we can have a speed up of the calculation. Okay. So now, we have seen that the semi-optimal basis could be defined for both the reducible pi 0 and the irreducible pi 0 here, the other one. Okay, and then the polarizability is defined in this way. Just in the rest of this lecture, I will, as in our code, I will just consider time reversal symmetric system. So all the wave function will be taken real. It's very important. That so here complex conjugate signs are not appearing. So the irreducible polarizability can be written like this. And as you see, we want to construct a basis for polar in real space on various conduction states. So we've done this in several ways. And finally, what is implemented recently is something like this. So one polarizability basis can be found by solving this equation, which, as you see here, what we calculate is just the polarizability operator at time equal 0, just we construct a product of valence and conduction states, and then we find a orthonormal basis set to span the most important part of the space, or to represent all this term. And what is done here is that we consider a maximal cutoff in energy. Then we can use an approximate form in which this operator here is the projector of a conduction space over of the conduction state up to a certain cutoff in energy is approximated with considering the space of the plane waves till a certain cutoff, and then the plane wave till a certain cutoff. These plane waves are projected over conduction state. What has been shown that in this way we can construct a restricted basis for the polarizability in a quite fast way. Okay. I will not go further on that.
The idea is to basically build a right basis so that you can.
Yeah, the basis which is more number of elements to represent.
When for any say, molecules and so on, you have suppose no information about what the basis should be.
No, no, exactly.
What should be the initial sort of guess where to start with? Of course, we know plane wave span the entire Hilbert space, but plane wave might not be good here because atomic orbitals or some molecular orbital theory might be accurate. So, what should be the sort of initial guess? Starting from in the darkness, you suppose start. How to reach into a sort of.
No, I mean, here we start from, so to construct the basis, we start from our valence wave function, and then from an operator like this that can be approximated in this way. So for producing the basis, first we need to calculate the valence wave function.
Where from? That's my question.
From a Constant calculation. So, I mean, this is so first we have to run just a simple self-consistent Constant calculation. And then we construct the basis for the polarizability, one way or another, and then we can start the GW calculation. Okay, so this is the basis has been done, and then just to say another thing that so we implemented this the calculation that we've seen before of the convergence with respect to the conduction state is being also obtained with this kind of optimal basis. One more thing important to say is that in the implementation we have done, we use the so-called analytic continuous function. This means that all the quantities we are calculating, polarizability of the reducible polarizability, the screen interaction, the screen Coulomb interaction, and so on, are calculated in imaginary frequency. This is done because these quantities are much more smooth on because we are far from the pole on the imaginary energy axis, and then we calculate the expectation value of the self energy on the imaginary energy axis. We do an analytic continuator procedure, and we find the expectation value of the self energy respect to the function state on the real energy axis. This is called analytic continuous approach. Okay, just implementing quantum espresso, and this is with a gamma sampling only. Okay, this is quite will be published in the next version of the quantum espresso. This first part. Let's go further. So we still have the problem. Let's suppose that so we found a basis for the polarizability, for the irreducible and reducible polarizabilities, and now we still have the problem of sums over conduction state, which essentially is killing us. We can proceed in this way. We use a procedure which is very similar to what we have already seen for density function perturbation theory, of perturbation theory in general. So mu and nu are indices of the polarizability basis, and this is the irreducible polarizability calculated in imaginary frequency, as we are here considering an AP continuation procedure. The extension to real frequency indeed is straightforward, but now we will consider just the analytic continuation frame. So this can be written in this way, in which just rewritten in this way. Here you see we have to sum over all the valence and conduction circuit. This is the picture. We can introduce two things. One is the projector over the conduction manifold, and to project over the conduction manifold, we just need to know the valence wave function, not the valence constant wave function. And then we use this notation here, which indicates a product in a real space at the point R of the constant wave function psi I R and phi nu R. Okay. So we can see here with a bit of algebra, which is easy, that the distance here of the irreducible polarizability matrix can be written in this way, in which for every valence state and every product with all the polarizability basis function phi nu, we have to project this product over the conduction manifold, and then we have to invert the Conchamp Hamiltonian. Consider also this additional diagonal term, which depend of the imaginary frequency where we want to calculate our irreducible polarizability. So, and this is an identity corresponding between the two, but there is so we could do this. This would work, but the problem is also much more computationally expensive. It's computationally expensive for two reasons. First, because we want to consider a lot of product here of valence wave function and polarizability basis functions, so too many products, and also we have to invert for several values of the frequency. So this is becoming quite too large to be done. And we have reduced using the two concepts that you have already seen. First is the concept of optimal basis, in the sense that so we construct a basis of function T0 alpha consisting in a limited number of functions, and with this limited number of functions we can represent with controlled accuracy all the product of valence wave function and polarizability basis projected over the conduction manifold. No? Now the problem is becoming that of solving this problem, so the problem of inverted Hamiltonian plus an additional diagonal term for each couple of T0 alpha and T0 beta wave function. Just in a moment I will come to the origin of this zero. Indeed, now the problem is that okay, we have reduced the basis, but now we have still to invert the Hamiltonian. Invert the Hamiltonian is something that every density differential code can do, but costs time. And we have to invert this Hamiltonian, this is the Conchamp Hamiltonian, for every different value of the balanced energy and also for every different value of the frequency. In my case it's imaginary frequency just because of the analytic continuation. And this is too much. But we've seen that there is the Lanczos chain approach, and we do like this. We start from we consider one of these elements T0 alpha. Just we kept the alpha fixed. And then, by means of the Conchamp Hamiltonian, we start a Lanczos change. This means that we obtain, by iterations, a series of functions, orthonormal functions, T alpha, T1 alpha, T2 alpha, T3 alpha, and so on. And in this basis function, started from each different T0 alpha, the Conchamp Hamiltonian is tridiagonal. This is because of the Lanczos alpha. As it is tridiagonal, means that calculating, inverting this Okay, solving this problem for different value of valence wave function, of valence energy, for different frequency, it means just we have to change the diagonal part of the diagonal matrix. This can be easily implemented, and also is very easy, it is very fast to be calculated. And this is how it's working. As we are in an imaginary frequency, in contrast with the lecture we have seen before, for TDDFT, a lot of Lanczos iteration are required. Here, in the order, a much smaller number, in the order of 15, 25 iteration are service. Okay, for the self-energy is something similar that can be, I think, I have to admit that it will be very obscure, but what we have to calculate in this case is an optimal representation, so a representation with a limited number of this S0 alpha function, and with this limited number we can represent this object, we are product of the constant wave function for which we want to calculate the GW correction. No? Can be the valence state plus the very first conduction state, which are multiplied in a real space with the polarizability basis phi mu, to which has been multiplied, as we see here, with the Bernoulli potential. Okay, I will not go further like this, but we have to calculate, for calculating them, finish our GW calculation, particularly for calculating the self-energy terms. We have to calculate first this basis for representing this term here, and then for every 0 alpha, so keeping fixed the alpha term, the alpha index, to generate a Lanczos chain, then to invert the constant problem at a different value of energy and frequency. Okay, just something can be interesting. That is, let's suppose that just to show how these optimal basis states can be obtained. So let's suppose that we start with a non-orthonormal set of states, psi I, and we want to represent this non-orthonormal state with an orthonormal basis set which has a limited number of elements, but retaining enough accuracy. So what we do, we calculate the overlap matrix, for every couple of psi I, psi j. Then we can solve with this matrix, we can solve the eigenvalue problem. So OK here is an eigenvector of OK here, the small one, is the eigenvalue. And then for obtaining orthonormal set, we define a cutoff over the value of over OK, or over the value of square root of OK, and then we just retain the elements, the OK, the K, which correspond to eigenvalue larger than a certain cutoff. The orthonormal states, then you can show this quite interesting exercise, are expressed in this way. So we have to take the square root of the eigenvalue, and then just to take a linear combination corresponding to the eigenvalue k of the starting non-orthonormal states. These states here are orthonormal, and so in this code that we have coded, we use a lot of these several times this algorithm to obtain optimal basis. Okay, for the benzene molecule, we see here that so this is the graph that we have seen before. So finally, we can do calculation without conduction state. I remember here, this was the extrapolated line. The three triangles were the calculated is 1,000, 2,000, 2,000 conduction states. This blue continuous line here was the extrapolated value, no? Because we have done before, we just could do the only thing we could do were fits. And here the black line is the experimental potential value, and we see here that we obtain a value. The purple line is the new calculated value without this method with Lanczos chain. We see here is in agreement with the previous extrapolation. Okay. Also, the rest, not only the ionization potential, but also the other vertical ionization potential, the other line corresponding to the other valence quasi-particle energy, are in good agreement with the experiment. So here we report the experimental ionization energy, and this continuous line would mean optimal agreement with the experiment. Here is the theoretical value. So the green, the black discs here are the results. And you see here that the GW results are in much better agreement with the experiment. Okay. So benzene, we are finished with benzene, and then we come back with the tetraphenyl porphyrin molecule, which is the starting point of this lecture. And here we see that now, here we record the experimental ionization potential, which now is in good agreement with our GWA estimate. So because as in this calculation we can select, if you want, the parameter in order to obtain a certain accuracy, we select in this case an accuracy corresponding to 0.15 EV. This calculation. Here we just compare directly our density of state with the state which is the red line with the experimental, in this case no synchrotron line, but helium UV line. So in this case, just for showing that the agreement with respect to the position of the peak here, which is the ionization potential. In this case, the experiment is done on an absolute scale. So they know the problem, know the origin, and then we can compare with the previous synchrotron data that we have shown before. And here we see that this also aligns in DFT. So here we have no reason to align of this feature, main feature here, and we see here a good correspondence. So this peak here is just entering this this line that this corresponds to the LUMO. So this okay, and here we see that we have a good correspondence for all the peaks. And if you want to compare now the two theories, go to the next slide. So here was what we get at the beginning with the LDA, and now is what we can calculate through the GW approximation. So finally, now we are able to reproduce photoemission spectra, and finally to help research, synchrotron research, in the sense of understanding that.
See, in the entire spectrum, which part of the spectrum we should look at very seriously, which carries the maximum information? Because if we look at the spectrum, in both cases there is underestimation and overestimation throughout. Right? We can see the peak do not really corresponds to.
I think that, but
where we should look at very seriously so that we can make a conclusion that this GWA is really going along with the experiment well. Which part of the spectrum we should focus very carefully?
Well, this is just a direct approximation density of state and the photoemission experiment, neglecting any oscillator strength, which should be small. I think that all the shape of the spectrum. There are also other factors which we are not considering. We are not considering thermal vibration that could enlarge the lines or the experimental lines, for example.
Can you go back 2 slides before?
I think that, yeah.
One result I would like. slide. Yes. Now you see that as in the lower part of the line, in the green dot as well as black dot, there is little variation in the points. But as we are going up, the slope is very smooth. Is it experiment is exactly corresponding to the theory? Is it an artifact, or just we see the points are little scattered in the lower part, right? The scattering, I mean the scatter of these dots in the lower part of the spectrum up to say 20 is bigger than as we go up.
So which
dots, you see the position of the dots, they are falling little. So every dot has a little scatter. You see, they are not fitting to exact straight line, right?
Do you mean that, I mean, there is no complete, I mean, there is very small deviation, quite small deviation with respect to the experiment.
But in the lower part, so what I am telling that if I see the, both the theory, GW as well as LDA, the scattering is very prominent in the lower part of the points. First 6 or 8 points. There is a scatter in the every data points, right? That is not very evident in the higher part. But maybe
no, wait, this is not the experiment, this is LDA.
No, that I am saying. In GW and LDA, if we look at first say 6 data points,
yeah,
the data points are not exactly fitting to straight line. Am I right? Average straight line, but they have a.
He's saying that the error is not fixed. It's a different amount of error for different.
Okay.
Why it may be due to in both the cases you see the GW and LDA, the error is exactly sort of a replica of each other in the lower part of the spectrum. Is it an artifact of some computation? Or?
No, understand. I don't know. Could be due to also to the fact, for example, that we are taking for simulated quasi-particle amplitude directly we just do this called diagonal approximation. This means that we are considering the LDA state, constant state, for the S quasi-particle amplitude. This maybe could be related to the fact that is a good point. Okay. 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 This is I think is what is the main message. So first that we can, once we have quasability basis, optimal basis, or efficient quasability basis, we can perform now GW particles energies without sums over conduction state obtaining conversion results. This is ABSC application to the system. So just to acknowledge my postdoc, Geoffrey, and Professor Big Chief Baroni, and my collaborator at MIT, Xiaofeng. Okay. Part of this very quite small part of this work has been published.